Okay. Who's ready to learn some deform? Good job, Garrison. Too late. Only one person gets to learn deform.
Can we last What's going on?
I don't know. It's a we have a volatile relationship. Question? So we're going into we started talking about the stresses due to bending. And really, even more important than understanding how to do these calculations is knowing when they apply. So, because if you don't know when these equations apply, it doesn't matter whether you calculate them right or not. You're going to use them at the wrong times. So remember that list of requirements that I gave you for using these formulas. Those are important. But then I started going into mathematical preliminaries, and there were two mathematical definitions. The first one was the neutral axis. And in the cross-section plane, the neutral axis is parallel to the z-axis. In other words, horizontal. And passes through the centroid. Okay, so for example, if you, neutral axis, N is for neutral. A is for axis. Okay, so say that this is your beam. It has a triangular cross-section. I did something in dynamics today, and it made my colors go away. And then I forgot to... Phew. I can only do it once then, and you can't see them. But that's a good idea. Okay, so the cross-section looks like this. And our coordinate system is this. So the neutral axis is in the plane of the cross-section. Where's the centroid on this shape? That's a cop-out. It's 1/3 of the way from here down that edge, and 1/3 of the way from here down that edge. So there's the centroid. It's closer to the, it's 1/3 of the way down there and 1/3 of the way down there.
So it's a right triangle?
Yeah.
Oh, I see.
What?
So you know how to equilateral triangle? No, it's right.
It's a right triangle.
It looks like it's an equals right.
I'm not trying to make this super complicated. I'm just trying to explain where the neutral axis is. That's the centroid. And so what do we see in the coordinate system looking at it if we're looking from this end? Here's us. What? Where do the axes go?
X is coming out.
Yeah, X is coming out.
Y is going up.
Y is up. Exactly. And Z is that way. And then this is the neutral axis. Okay. Now the next definition we need is the area moment of inertia. About an axis. People just call it the moment of inertia, but that's a fraught with pitfalls. So think of it as what it is. It's the area moment of inertia about an axis. And it measures how resistant to bending the beam's cross-sectional shape is. So it's just a geometric thing, but it determines how easy it is to bend this beam. How resistant to bending the beam's cross-sectional shape is. And before I go into what it is, this is a really important thing to notice. This is not the same thing as the mass moment of inertia from dynamics. And from Physics 1, you talked about that a little bit too. Even though they're both called, or both, I guess, denoted capital I sub A, so that's a nuisance. They're both called the moment of inertia. And they both have a parallel axis theorem. So it's easy to get confused about those two, but you have to remember those are different things. So here is the definition of the area moment of inertia. And if you look at the definition of the mass moment of inertia, it looks very similar, except you replace mass with area in the formula. So the moment of inertia about let's say moment of inertia about an axis is equal to the integral over the cross section of y squared dA. Where y is the distance from the axis to the infinitesimal increment of area. So infinitesimal area dA. Well, it's not really, this isn't really limits, it's just saying you have to integrate over the entire cross-sectional shape. So you can do that a bunch of different ways. You can sometimes, you could do it as a double integral, or you could figure out some clever system where you're doing it as a single integral. But either way, you just have to integrate over the whole cross-section. So let me do an example calculating the, so how often do you think you're going to have to use the integral formula? This one time. You have to watch me do it. But then after that, we're just going to use formulas just like with the mass moment of inertia. Yeah, I guess you don't have to watch me.
Does that happen all the time in real life, or is it just class?
I mean, I suppose it depends what the application is, but I'd say if you took all the people calculating area moments of inertia and then did the statistics on it, then most of the time people are using formulas. Okay. Integral example. Yeah, well, I think the thing is when you make computers do it for you, you break everything up into rectangles, and then it's easy. You just have to do it a million times, you know. Okay, so find, yikes, what was that? The moment of inertia, the area moment of inertia, formula for a rectangular cross-section where A, so this is moment of inertia sub A, where A is the neutral axis. Okay, so here's the rectangle. This is the neutral axis. So the neutral axis goes along with the z-axis, and it passes through the centroid of that shape. And we'll say that this rectangle has a height h and a width w. And to do the integral, we're going to break it up into slivers like this. So this is an infinitesimal area. With a thickness dy. And a height of y. And so we have the integral of y squared times the increment of area corresponding to that height y. So if this sliver is our increment of area, what's our expression for dA? Yep, w dy. Anybody have any questions about that? On these, it's funny teaching these classes where like you guys take 3 classes from me because I say the same things over and over again. It sounds smart the first time, but it sounds dumb by the 3rd time you've taken a class. But what?
I got a question.
Okay.
So you always just make z-axis your neutral axis?
Yes.
And we just decided, let's see, that, well, could you have made the neutral axis the vertical on this? Or it's always horizontal too?
Okay, that's a good question. So if you have a beam, it depends which way you're bending the beam. Okay? If we were bending the beam side to side, you know, if that was the same beam and that was the cross section, but something was pushing on it this way, we would really just flip the coordinate system and still treat it like it's vertical.
Okay.
So we're always going to calculate these area moment of inertia vertically like this. The neutral axis is always going to be horizontal. Otherwise, we just flip the shape. Yep.
Neutral
It's the whole z-axis plus and minus. And actually, it's called the neutral axis because you think of it in the cross section. But if you take the neutral axes for the whole beam, it's really a plane. Okay, so what I was going to say that many of you have heard me say in 2 classes before this is whenever you have these integral definitions, the trick to using these is coming up with a clever way, a good, efficient way to design your increment of area, whatever your increment is, your increment of mass, increment of area in this case. So that's something that's going to keep coming up in your engineering classes. And if you can kind of make sense out of this sort of thing, you'll be ready to make other people feel stupid in your future classes. This is a WDY. Yep, this is our DA. And once we chose that, we were set up to make this problem pretty easy. If you didn't see that this is a good way to define it, this problem is hard, you know. Okay, and then what are the boundaries? We're doing it in terms of y. So, yeah, let's go 0. Let's go negative h over 2 to h over 2, actually. Okay, so width is constant, so you can pull that out. And so now you just have y squared dy. So you have width times y cubed over 3, evaluated from negative h over 2 to h over 2. So that's w h cubed. So WH cubed over this is 8 and then 24, right? 2 cubed is 8 times 3 is 24. And then minus negative WH cubed over 24. And so the formula is WH cubed over 12. And in a list of formulas for area moment of inertias, this is the formula for a rectangle.
Would you have to go from, would it have been wrong to go from 0 to h?
It would, because we need our y to represent a distance from the neutral axis. Yep. Okay, so one thing to notice about this is what's more important for preventing this shape, this beam from bending, the width or the height? Yeah, the height is way more important. For resisting bending. Than the width. So we're going to use this rectangular shape a lot. We're also going to use a circle a lot. Mm-hmm. Well, think about this. This is a beam. right? Is it more resistant to bending this way or this way? You know, so that's what this formula is telling you. It's hard. It's really hard to bend even a sheet of paper when it's oriented this way, to bend it down. It's really easy to bend it. It's hard to keep it from bending when it's like this, you know. That's because when you're holding it like this, the H is a fraction of a millimeter. When you're holding it like this, the H is a foot, you know.
So when you're holding like that, even if the paper was like way wider,
Right.
it'd still be pretty easy.
That's right. That's right. So the other shape we'll use a lot is a circular cross section. And so the area moment of inertia of a circle about its center, about its neutral axis, is equal to pi radius to the fourth over 4. An example?
Any real example?
Okay, so SI units for area moment of inertia. I know some of you are still skeptical about these two things being different. Do you remember what the units for mass moment of inertia are? Kilogram meters squared. This one has units of meters to the fourth. You can see that in both of these two formulas. Okay, so I've only given you two shapes for area moments of inertia. There are two mathematical facts that are going to make this more useful. That make those formulas above more useful. The first one is you can add or subtract moments of inertia of simple shapes, simple cross-sectional shapes, to build up complicated shapes. The trick is, just like with mass moments of inertia, you have to remember that for your simple shapes that you've broken it up into, you have to calculate their area moment of inertia about the neutral axis of the entire complicated shape. Okay? So just remember you have to calculate the moment of inertia of the simple shapes about the neutral axis of the complicated shape. Okay, so how do you do that? That's the second fact that makes these more useful, is that these follow the parallel axis theorem. So if you're taking, okay, so let's say that your axis, so if the axis A is not the shape's neutral axis, then the moment of inertia of the shape about A is equal to I about the neutral axis plus the area of the shape times d squared, where d is, the distance between the neutral axis and your new axis A. Parallel axis theorem means A and NA have to be parallel. Okay, so let me do an example. So let's say that we have an I-beam. And our coordinate system has the x-axis pointing that way, y-axis up, and the z-axis towards us. And I'll give you the cross-section dimensions. So let's say this, that's called the flange. I think that is right. And this is called the web. Let's say so the flange is 0.5 meters. The web is 0.5 meters. And let's say these are all 1 centimeter. I know 1 meters, everything. Okay, the neutral axis is this. We know that just by symmetry. To find the neutral axis, I mean, you know it's going to be horizontal. You just have to find the centroid, and we know the centroid of this shape because of symmetry. Okay, so that's the axis. And we're going to break this up into 3 separate shapes. So first, the top flange. Well, the moment of inertia about its neutral axis is 1/12 times the width, which is 0.5, times the height, which is 0.01, cubed. And then we have to use the parallel axis theorem. So how far, what's the distance from the neutral axis of this top rectangle to the axis A? 0.25 plus another 0.005, so 0.255, right? And the area is, so the area is 0.5 times 0.01, and the distance is 0.255 squared. And you end up with, I think, 3.25 times 10 to the minus 4 meters to the fourth. For the bottom flange, we have the moment of inertia about the bottom flange's neutral axis. That's this. Then the parallel axis theorem. What's the distance for this one? Yeah, it's the same. It's symmetric. So 0.5 times this should have been 0.01. 0.01 times 0.255 squared, and you get the same thing. And then for the web, the moment of inertia, so the neutral axis for the web itself is the same as the neutral axis for the entire shape. So this is just going to have the main formula for the rectangle. So 1/12 times the area, 1/12 times the width, which is 0.01, times the height, 0.5 cubed, and you get 1.04 times 10 to the minus 4 meters to the fourth. So the total area moment of inertia is, you can think of it as like I1 plus I2 plus I3, and you get 7.55 times 10 to the minus fourth. Yep.
It doesn't really make sense because you think the one with the web in the center would have a bigger than the two outside ones, right?
Yeah, you know why it doesn't? That does seem strange. But it's because if you think about what that formula, it says you get a big value you get a big value for the moment of inertia if your area is concentrated a long way away from that neutral axis. And so those two flanges are positioned as far as possible away from the neutral axis. And actually, that's why they use I-beams, is because you can take a relatively small amount of material, concentrate a big chunk of it far away from the neutral axis, and it resists bending a lot better than it would if you took that same amount of material and just turned it into a circular cross section. Also, like, I don't know if you've ever noticed this, but on bicycle frames, steel bicycle frames have very thin tubing. But if you look at an aluminum or a carbon frame, materials that aren't inherently as strong as steel is, per weight, those tubes are way fatter. And what's the reason for making them fatter? It's because if you concentrate more of that area far away from the neutral axis of the tube, you can, even though the material isn't as strong on its own, you can make that shape, make it more resistant to bending, less prone to bending. Okay, so that you can see that in pretty much any application where something needs to be resistant to bending, it's been engineered in a way to move area far away from the neutral axis. Well, yeah, those are sort of, yeah, right. They make those sort of in an I-beam shape. So, yeah, I'm sure you're right about that. Okay, so now we have that. We can finally go to, so finally, the stress due to the internal bending moment in a beam. Remember last time I did that drawing where I showed how if you look from the side of a beam that's being bent, I colored the top red, I think, the middle green, and the bottom blue or something, and I showed that the one of those lines that's closest to the center of curvature of the beam is going to be shortened. The one that's farthest from the center of curvature is going to be lengthened, and the neutral axis is going to stay the same. And because of that, the only stress that we get from bending is an axial stress. It seems a little odd at first, but when you think of it in terms of that shortening and lengthening of lines, it makes more sense. So sigma xx is equal to negative m times y over I. And you can just trust the sign on this one. You don't have to think about directions outside of this.
Y is what now?
Okay, so m is the bending moment. That's the bending moment that's an internal load for the beam. I is the area moment of inertia about the neutral axis. And y is the y coordinate of the chosen point where y equals 0 corresponds to the neutral axis. Okay, is there any way I can make this problem faster? Okay, so let's say that we have this beam, and the only loads acting on it are let's say there's a couple of 200 Newton meters on each side. And maybe we better just do that for now. No, let's do this too. Okay, so let's say it's also in tension, 1,500 newtons, 1,500 newtons. And here's the cross section. It's a square, 0.2 meters tall and 0.2 meters wide. And let's calculate so right at the midpoint, let's calculate the stress tensor at the top, middle, and bottom of the cross section. Okay, so first let's get the tension part out of the way. That's not going to change based on what point in the cross section we choose. So so first we're going to break this up into a stress tensor due to tension and a stress tensor due to bending. So let's start with the tension. This is going to be the same for all 3 points. The internal tension, you could do a internal loads calculation, but this whole thing is in tension of 1,500 newtons. So the XX stress due to the tension is positive 1,500 divided by 0.2 times 0.2. Can someone tell me what that is? 37500. Okay, and that's pascals. And so the stress tensor due to tension is 37500, and then zeros everywhere else. And now the one due to, and that's the same for all 3 of those points. So now we'll go to bending. The internal bending moment for all of these is just equal to, again, we could go through the internal loads calculation, but this is just going to be negative 200 Newton meters everywhere. The moment of inertia is 1/12 times the width times the height cubed. Can someone calculate that one? Okay. And so now for these 3 points. Now those 3 points are going to have different values due to bending because that y value is going to be different for all 3 of those points. So first A, I think I said that's at the top. So sigma xx is going to be negative bending moment times y. What's y for a point at the top? 0.1, yep. Divided by 1.3 repeating times 10 to the minus 4. So what do you get for that? Oh, and this should be a double negative.
150,376.
Okay. And so for a total stress tensor at the top, that's the stress tensor due to tension plus the stress tensor due to the bending moment.
I got a different number. I got 153,826.
That's pretty close. That's close enough for 2 minutes left in class. Okay, so that stress tensor due to bending is 150, 376, 0 everywhere else. And so what do you get if you add positive 37,500 plus 150, 376? Ooh, 187, 876. Okay, second, what about the middle? That's right, yep. Because you have the negative bending moment times what's the y coordinate at the middle? 0 divided by I. And so you get 0. And so the total stress tensor is just 37,500. Is that what it was? And then the last one, sigma xx is equal to negative 200. What's the y value for the bottom? That's right, negative 0.1 divided by 1.3 repeating times 10 to the minus 4. And so you just get negative 150, 376. So the stress tensor due to bending is negative 150, 376, and then zeros everywhere else. And so the stress tensor at the bottom is the one for tension plus the one for bending moment. And what do you get for this one?
112,876.
Negative 112,876, and zeros everywhere else. So where would you be most concerned about fracture beginning in this beam? Top or bottom is generally the case, and in this case it's the top, because in the top we have an additive effect of the tension stress and the bending stress, and at the bottom we have those counteracting each other somewhat. So you're most likely for this to fracture at the top. Okay, and then from there you could calculate max shear, you could calculate the strain, all that kind of stuff that we've done with stress tensors this whole class so far. Okay, that's it.